Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning probably. But actually, I record this video at night actually. So let's continue on the next topic on the separation methods, which is the planar and classical column chromatography. So basically, we will look into two parts, which is first one is planar and then classical. Okay, in the planar, we will look into the paper chromatography, okay, and also the TLC, or we call as the thin layer chromatography. So most of the slides is actually prepared by Dr. Amy Shazwani. I just modified a little bit just to enhance the information, okay, based on my humble knowledge. Let's go. The first thing always we begin with the definition. Okay, column chromatography take place inside a tube. Okay, so we imagine, okay, in the column. Okay, so the column made of tube. Okay, I'm not very good with the what we call the 3D. Okay, so basically this column, okay, should be vertically lah. Okay, right now I just draw it horizontally, so it's not a correct way how to perform the what we call column chromatography. Column chromatography always vertically, and we spread the compound descending. It means that from upper to below. Okay, based on the gravitational flow, or we can use pump to push our compounds to separate. Okay, and then the second one is the planar chromatography. Okay, planar chromatography is defined by having the stationary phase, okay, stationary phase of the process take place on a plane. So the keyword here, stationary phase, okay, of the process of the chromatography or the separation, okay, take place on a plane. What is mean by plane? It's mean like a plane, 2D. 2D plane is two-dimensional that we can imagine, okay, such as like a paper, okay, or we can also imagine as plate. Okay, so the planar chromatography is defined that the station phase of the process take place on the column. Take place in a plane. Okay, that is planar chromatography. Okay, column chromatography inside of a tube, or you can say as the inside of a column. For the planar chromatography, okay, take place on a plane. Okay, so hopefully if the question asks, okay, please provide the description of the column and the planar chromatography. Okay, you guys can answer it very well. Okay, let's continue. Okay, the next one, okay, is just the description. Okay, basically the planar chromatography is not, it's not only planar chromatography. Here is the planar chromatography and column chromatography. Okay, it's actually fall under liquid chromatography. Okay, so under the liquid chromatography, okay, we can look at under liquid, okay, stationary phase, and this solid stationary phase. Okay, so maybe you can have the some of the confusion later on, but I will describe why actually the plane, okay, the plane one, the paper, you looks like a solid, but it's actually the liquid. It means that the partition chromatography. Okay, I believe you guys get confused right now. Okay, I'm not sure if it's the first time you heard these terms. Okay, partition chromatography refers to the one that have the liquid to immiscible phase. It means that liquid. Why my pen is not working? Okay, partition is liquid. Okay, liquid phase. For example, liquid stationary phase, okay, liquid mobile phase, and also the liquid stationary phase. Okay, the above one here is the what we call the mobile phase. The second row here, okay, is referred to the to the stationary phase. Okay, in the chromatography, if Dr. Faizwan already described, or maybe you guys are not introduced with, Okay, chromatography can be divided into the affinity. Okay, it can be divided into adsorption. It can be divided into the partition. Okay, okay, and a few others, if I'm not mistaken. Okay, if the separation is between liquid and liquid, okay, the mobile phase is liquid and the stationary phase is liquid, we call as the partition chromatography. If the interaction is only on the surface, okay, so we call as the adsorption, okay, which means as like liquid and also solid. Okay, liquid and also solid, we call as the adsorption chromatography. Okay, if you look over here, okay, before we going more further, I just want to go back to our topic. Okay, in planar chromatography and column chromatography involve both liquid and solid. Okay, for column chromatography is only involve liquid solid chromatography, which means that only the adsorption type of the separation, where in the column, okay, the adsorbent is the solid that we put inside of the column. Okay, for the plane chromatography, okay, where we have the solid one, okay, uh, solid stationary phase, okay, where actually we deal with the TLC, okay, when we deal with the TLC, say, so usually is the solid. Okay, we deal with the solid stationary phase. So it's liquid solid. So most of the time is adsorption, AD, adsorption chromatography. Okay, so when we use the paper chromatography, so we will deal with the liquid. Okay, I will tell you later on why paper chromatography, even though the paper it seems like a solid thing. Okay, so but in this scenario we call as the liquid chromatography. Okay, for the paper it's not the adsorption, but we call as the partition chromatography. Okay, okay. So basically the thing that we can ask you guys, okay, please describe the nature of the liquid, okay, liquid chromatography on the planar. So you should guys be able to state that planar chromatography is part of the paper chromatography is part of the partition chromatography, or what we call as the liquid that contain the liquid mobile phase and also liquid stationary phase. For example, please mention the what is the nature of the TLC. Okay, you can say the TLC is made out of solid stationary phase and using the mobile phase, liquid mobile phase as the eluent. Okay, for the column chromatography, it's about the same with the TLC, where the stationary phase is solid and the mobile phase is liquid. But for the paper chromatography, the stationary phase is the liquid and the mobile phase is also liquid. Okay, that's why. Okay, that is the thing that you need to understand later on. Okay. Okay, here is the example of the paper chromatography. Okay, so we just go into the planar chromatography. Okay, which is the first part. I will focus on the paper chromatography, and later on I will go to the thin layer chromatography. Okay, here is the example of the paper chromatography. Okay, okay. The principle of separation in the paper chromatography is partition chromatography. Why we call as the partition chromatography? Because the analytes are separated based on the interactions between two non-miscible liquid. Okay. Of course, you guys imagine, okay, it's a paper actually, right? Why we say that the interaction between two non-miscible liquid? It's not that the interaction is between the liquid and also this solid stationary phase. We will look into that later on. Why actually? Okay. The main difference of the paper chromatography is that a sheet of paper is used for the inert phase. Okay. The sheet of paper is used for the inert phase. It means that it's not actually interact with the like the paper itself. But we look what actually in the paper chromatography interact with the analytes. Okay, the paper usually contain pure cellulose. Okay, so the paper contains pure cellulose and no lignins, copper or other impurities, and is available in strips or sheets. Okay, low porosity paper will produce a slow rate of movement of the solvent, and thick papers have increased sample capacity. So if the paper is low is content of low porosity, it will produce a slow rate of movement. Okay, if we have a thick paper, then we can increase the sample capacity. Okay, so let's look on the stationary phase of the paper chromatography. Okay, here, okay, here is why actually why is the paper chromatography fall under partition. Okay, which means the interaction between two non-miscible liquid. Okay, because actually that the analyte is not actually interact with the cellulose. Okay, the analytes interact with the water that actually fill in the space in the paper fibers. So you can imagine that inside of the paper you have all the cellulose that actually bonded with the H2O. H2O is actually fill the space of the cellulose. Okay, so actually your analytes interact with the H2O that bonded to the cellulose. H2O is made up of liquid, right? Even though we cannot see by our naked eyes, but this is the interaction actually made by the paper chromatography. Okay, because it's not directly in contact, the analytes, for example, your analyte is not directly in contact with the cellulose, is contact with the H2O. So that's why, okay, we say that the stationary phase of the paper chromatography is also liquid, and that is the reason why we call the paper chromatography is the partition chromatography. Okay, hope that settles the confusion. So basically, there's some of the question may can ask you, okay, please describe the stationary phase and mobile phase for the paper chromatography. So you need to be able to describe. For example, okay, the stationary phase of the planar chromatography used in this study is the liquid. So can you state what kind of the planar chromatography that is actually used? So you need to state it, that is paper chromatography. So that is the kind of idea what kind of the question can be asked. So I can actually adjust it to more harder question. Okay, for example, okay, in the study we cannot actually what we call the adsorption towards the station phase is not that great. So you need more polar interaction of the planar chromatography. So what kind of the planar chromatography that you could suggest to replace the one that actually used in this situation? So you can suggest a paper chromatography. Why? So the water is tightly bound in the interspace of paper fiber, so it will produce a kind of partition chromatography. That's second point. Okay, because of water high in polarity, so it can give a better interaction in terms of the polarity. So that is the kind of idea. Okay, why actually how to answer that kind of the question. Okay, let's go to the mobile phase. Okay, basically the mobile phase is about the same with the TLC. Later on, we will look into the thin layer chromatography. Okay, mobile phase is any solvent that is partially miscible in water. Okay, if we use the one that is actually miscible in water, so the problem with it that it will interact a lot. Okay, choice of the solvent will depend on the nature of the substance to be separated. Often a mixture of two or three solvent is required. So basically, if we want our mobile phase to move faster, okay, so we need to use non-polar and non-polar solvent, for example. Okay, but for example, we want our analytes to move faster. Okay, then we need to use more polar solvent. We need to use more polar solvent. Why? Okay, because the polar solvent. Okay, the polar solvent will interact with the stationary phase stronger, so it will replace the analyte faster, so analyte can go upwards faster. Okay, so let's go one by one here. Okay, choice of the solvent will depends. Okay, we already described. Offer a mixture or two, three solvent is required. Sometimes we modify, not a pure solvent. For example, we not using pure hexane. We are not using, for example, pure methanol. Sometimes we adjust to adjust the speed of the what we call the paper development. Okay, later on we will discuss how actually we perform the paper chromatography. Maybe after that you can come back to this slide and read it later after you understand how the flow, how to actually perform the paper or TLC later on. The analytes that are highly water soluble or have the greatest hydrogen bonding capacity will move slower along the paper, while less polar compounds will travel faster with the solvent. Okay, so as we know that water actually bonded with the cellulose. So if the compound is polar, so it will more attach stronger to the water. Okay, or the stationary phase of the paper chromatography. So if your compound is polar, okay, so it will interact more. If your compound is less polar, so it will less interacted with the stationary phase, so it will go faster. Okay. Okay, here is the example how we actually set up. Because of the paper chromatography, okay, the paper itself is not that sturdy. It's not that what we call have the uh, it is actually less flexible. Okay, so we need to have a great support. Okay, so what you can do, you can hang the paper, or you can curl, and then you can put vertically, so you can give it more flexibility. Okay, if you just put at the chamber, it's not like a plate, it's just a paper. So what happen, your paper will curl over. So we don't want that to happen. That's why uh, there are only two methods, okay, which is hang and also put the paper vertically. So if the question asks you what is the two, okay, methods to what we call set up the paper chromatography, okay, here is the two. So that is the kind of the question. Maybe the question, okay, please illustrate how to actually what we call to set up the paper chromatography. So you need to know how to do this. All right. So later on, I will show you how to actually the procedure of the paper chromatography and also the TLC is about the same. But right now, I just want to describe the paper chromatography and the TLC. What are the differences? And later on, I will show you the how to develop, okay, paper chromatography and also TLC. Maybe later, maybe I will focus on the development first, and after that, we will go to the differences between them. Okay. Okay, let's go to the next slide, which is the forgive me about the spelling, is Telechromatography and its application. Okay, the TLC have the same basic principle with PC. Instead of using cellulose paper, a flat inert plane is coated with an adsorbent such as silica or alumina. The basic principle is kind of the expression on the planar. Okay, so as the movement is between two stationary between two, which is the mobile phase and also the stationary phase, but in the TLC is not the partition chromatography. In the TLC, is adsorption chromatography. So you need to know the differences between TLC and also paper chromatography. Okay, the more that you have in your mind, you understand the differences between both of them, I think you can understand it better. Okay, in TLC, component of the mixture are separated between adsorbent, okay, and a mobile phase, which flows through the absorbent. Okay, the station phase compared to the paper chromatography, okay, the stage phase made of silica, is not made of cellulose, and there is no bond H2O. Okay, chromatography is important technique for identification and expression of organic compounds. Okay, here is the applications of the TLC. Okay, so the principle is about the same. Okay, just okay. It's about the same, but it's the absorption, and here is the principle. So if for example we ask you to describe what is the TLC, so you may get 1 mark, 2 mark, and 3 marks. Okay. So the next thing maybe we can ask you guys that I need you guys to be able to understand the application of TLC. The TLC and also the paper chromatography, they have four applications. They have four applications, but paper chromatography is the old technique actually. After the paper chromatography, the TLC is developed, where the TLC is much more versatile compared to the paper chromatography. Today's the paper chromatography just for basic screening only, but it's just it never used for that these particular things. So basically paper chromatography just want to make sure want to know how many components, but they don't really use that the paper chromatography for further analysis. Okay, so basically the TLC is the most common thing that used in the for especially in the organic application. Okay, so there are four applications, okay, in the TLC. Okay, first, identification of components of mixture using appropriate standards. Okay, so we want to identify the components of the standard. Okay, how actually can I explain to you guys? Okay, the best thing that I can do, maybe, sorry, maybe I just, okay. Okay, let's go to the first one, identification of component of a mixture. Okay, for example, here is your TLC plate. Maybe I can draw a larger one. Okay, man. Okay, so maybe here is the TLC plate. Okay, here you put the standard. Okay, maybe you put drug. Okay, what kind of the drug famous? Okay, for example, cocaine. Okay, is the standard that you have. And then you have sample, okay, you seize from a drug addict. Okay, maybe you seize here from a supplier. Okay, maybe here is the standard of the amphetamine. Okay, amphetamine, for example. Okay, here is maybe come from what? Drug addict, right? Okay, here is from the supplier. Okay, maybe here what kind of the amphetamine, cocaine, morphine. Okay, just put over there. Say, for example, you have three standards, 1, 2, 3. Okay, you can put other way around. It's up to you. Okay, so after the TLC process, you can see the movement of the spot. For example, in the cocaine, okay, because okay, usually the pure standard, okay, they will produce one spot. Okay, they will produce one spot. One spot maksudnya satu titik saja. But for the sample, they may produce fuse. Okay, for example, the cocaine, the spot is this location. Okay, for the amphetamine, maybe it goes higher. Maybe for morphine, it goes lower. Okay, so maybe from the drug addict. Okay, from the drug addict. Okay, because okay, usually the one that sell, okay, to the drug addict, or the one that available in the market is not that pure. If for example it's really pure, okay, it's supposed to be sell at higher price. So usually about less than 70% purity. Okay, so that's why I would like to suggest you guys to watch the Breaking Bad movie. Sorry, not movie. Okay, of course the Breaking Bad have the movie, right? Okay, but I would like to suggest if you want to fall in love in chemistry, please watch the Breaking Bad series. Okay, just put that aside. Okay, for example, we obtain the sample from drug addicts. Okay, the one that available in market usually is made of impurities, not really pure. Maybe it has 2 spots or 3 spots. Okay, maybe it has 3 spots. Okay, okay, okay. And then for the one in the from the supplier, okay, maybe the supplier is not the same one that actually supplied to the drug addict. Maybe produce the other impurities. Okay, for example, okay, here, okay, here, yeah, okay. Okay, if we look over here, the drug addict, okay, for example, okay, this one about the same level lah. It's the same level, okay, maybe because I'm not a good drawing, so we can say that in the drug, okay, the sample from the drug addict, okay, so from the TLC analysis, we can say that the drug addict sorry, the sample from the drug addict also have the cocaine, and also what is it, morphine. Okay, how about this one? So we don't know what is this. Okay, so we cannot identify this one, but we can say from drug addict we can obtain it has a mixture of the what we call the morphine and also the cocaine. Okay, how about the one obtained from the supplier? Okay, the one that sell the drug, but maybe not selling the same drug to the drug addict. So if we can see also from here, this is unidentified. Okay, how about here is also unidentified. Okay, but in the from the supplier is matched with the sample. It matched with the amphetamine. So we can say that from the supplier is obtained amphetamine. Okay, and also what kind of the other conclusion that we can say? Okay, the other conclusion that we can say, okay, the one that actually sell by the supplier is not the same that actually have obtained by the drug addict. So maybe the other supplier actually sell the drug to the drug addict. Okay, so if basically it come from the same supplier, the drug obtained from the same supplier, they should have the same pattern. Okay, they should have the same pattern. But right now the pattern is different. So the drug addict obtained the drug somewhere from someone else, not from this supplier. Okay, not from this supplier. Okay. So that is the kind of information that you could obtain. Okay, let's look at the second application. Okay, and then we want to following the cause of reaction. Okay, want to know if the reaction, okay, is it complete or not. Maybe sorry, maybe I can just discard. Okay, this is better. Okay, I just click. So let's look back at the second. Okay, the cause of reaction. For example, uh you are in the industry that synthesis the compound A. Okay, use synthesis of compound A to compound D. Okay, the compound D. So you know that from A compound, okay, you want to synthesis until it reach the final compound, which is the compound D. So it will have the compound B and compound C. So for example, okay, you have the TLC, okay, you have the standard B, A, sorry, maybe you have the sample. Okay, you have the A, standard A, you have standard B, you have standard C, you have the standard D. Okay, for example, okay, for example, it's required that the process, you don't know actually is if your analysis is complete or not. Okay, for example, after what we call programming the machine, okay, to process the standard, okay, the material A, okay, for about 20 hours, so you still don't know is the reaction is complete or not. So you run under TLC, and then for example you observe that, okay, maybe B here, sorry, A here, B here, C here, D here. Maybe, okay, at the 20 hours, okay, after you run the TLC, the spot move to here. Okay, sorry, what happened? Okay, move to here. It means that your sample only, the process only reach up to D, C. So here A, B, C, right? So the process is up to C, so it's still not complete until to D. So you need to further continue the process of the synthesis. So that is how we actually can use the TLC, okay, based on the second points of the application. Then the next thing is analyzing fractions collected during purification. So you want to analyzing fractions collected during purification. For example, okay, what is the favorite food of the Malaysian? Malaysia. Okay, okay. For example, durian. Okay, you want to know what exactly compounds in durian. Okay, what exactly compounds in durian make we love with durian. For example, maybe you uh do the organic synthesis, you try to purify the compound, and then you want to identify how many compounds in durian, for example, at the TLC, okay, and then you run under the spot. Maybe after running the TLC, you can observe, okay, actually, oh, we have 3 compound in the durian, okay. So what is the actually the compound for this thing? So then you can submit for further analysis using GCMS or LCMS. Okay, so that is how the third application of the TLC can be utilized. Okay, and then of course the last one, to analyze the purity of the compound. Okay, for example, okay, you say that you process from you would like to extract the compound, only compound A from durian. Okay, so you said, you claim that, okay, you claim that only your method is able to only extract compound A. The other impurities you will not be extracted using your method. So that is your claim. So how to actually be able, okay, to support your claim? So what you can do, okay, then you put your spot of analysis, and if the spot spotted, okay, by you only one spot, it mean that your whatever synthesis over here is pure. If you have, for example, you have several spots, it means that your extraction methods have a lot of impurities. It means that your extraction method is not that successful. So that is how, okay, we are able to utilize the TLC. So hopefully you will be able to understand. Okay, so the kind of the question. Okay, for example, please state the application of the TLC. You can just state. Okay, we just state here and here. But for example, please explain, okay, 2 applications of the TLC. Okay, for example, please explain. So you need to not only state, so you need to explain. For example, please explain, or please discuss, or please give example 2 applications. So you need to be able to give examples of the TLC. For example, you have identified 2, so you need to give appropriate example, or maybe you need to give appropriate example to explain how actually the TLC could be applied, okay, in the real applications. Okay, that's it, I think, for the applications. Okay, here is how you put the spots, and then will be separated. Okay, maybe here is obtained. Okay, maybe here is the comparison between 2 inks, two gel pen. Okay, so we look over here. Some of the spot, maybe it says, may come from the same compound, the other may maybe come from the different compound. Okay, here is the example of the TLC setup. Okay, TLC system showing glass through at the plate, side view showing solvent vapor, saturated view, front view. Okay, here is the side view. Okay, here is the front view. Okay, if you look over here, okay, the thing that I need to remind you, okay, for example, you spot at this line, your solvent level never exceed this line. Okay, must be lower than the spot that you spot your sample. Again, the solvent you use as the mobile phase, the amount, okay, the volume must be lower than the height where you spot your sample. Okay, I need to. So here is the front view, here is the side view. Okay, here is the TLC plate. Okay, the stationary phase. Okay, and of course here we have the solvent, and then we need to use the cover. Okay, so the question that can ask you, why the solvent must be low compared, why the solvent level, okay, must be low compared to the level of spotted. Okay, that is the kind of question that can be asked. So I would like you guys to be able to answer. I will left this question to further in our discussion later on. And the other question, why we need to put cover, why we need Why my pen is not working? Why we need to cover our system, or we can call this as the chamber. Okay. Solver weighted paper is not necessarily, to be there. It's not necessary to be there. The one that is really compulsory is the chamber over here. Okay, and then we need to cover. Okay, we need not to allow any solvent escape. So these two question, okay, I would like to left it to you guys. Okay, in our discussion later on. Okay. So this is the item that you need, maybe a pair of beaker, okay, and then we can use the petri dish, okay, to cover, or wash glass to cover our measuring cylinder. Sorry, measuring cylinder. I'm a little bit sleepy right now. Want to cover our beaker, and then okay, using the capillary tube, we spot our sample. Here is our sample. We put dip our capillary tube over here. Capillary tube is very small. Okay, so you just can put here and then spot. Okay, and then you can set up. Okay, in the chamber. Okay. So before we going further to the procedure to develop the TLC, okay, let's look into the basic components like the paper chromatography. What is the solid phase? What is the stationary phase? What is the mobile phase? Solid phase, of course, the okay, usually consists of material coated on glass plate or aluminum sheets. Okay, nowadays for the TLC also you can found, okay, the basic or the plate is made up of plastic also there. Okay, the thickness of the coated material is usually 0.2 0.25 mm. Okay, please, I don't want you guys to remember this thing. Okay, so no need. Okay, this one you no need to remember the exact. We just it's just coated materials like such glass, silica or alumina. Okay, the base material is the glass plate, aluminum sheets, and also the plastic. Okay, also that. Okay, but you don't need to remember exactly 0.20, 0.25 here for the coated material, no need. The solid phase particle are usually fine with diameter less than 50 micrometer. Don't need to remember exactly. So you just said fine particle also enough. Okay, silica gel is the most widely used in the solid phase of TLC. Okay, here is why silica gel, okay, is more preferable compared to the alumina. Okay, in alumina later on, okay, here is why there is a one of the reason lah. Okay, silica has high surface area compared to the alumina. So when we have the thing that have the high surface area, it can provide more interaction. Okay, that's why the silica gel is much more versatile compared to alumina. But of course, the other reason, okay, silica gel also we can derivatize the active site. Okay, we can produce multiple kind of active sites, so it can react with many more kinds of compounds, okay, compared to alumina. So that is the other reason. So maybe I will not discuss the detail of the why silica gel, okay, is commonly used compared to alumina, but I want you guys to find about it. Okay, why the silica gel is widely used in compared to alumina. So in the next discussion, I will discuss again. So I need you guys in the discussion later on, 1 hour discussion later on. So we will discuss about this first, and I hope you guys ready, okay, with the answer. Okay. Active sites that can interact with the solid consist of the Solana groups at the distance. Okay, no need about the distance. It's not. I don't want you guys to remember exactly about this. This will not be asked in your examination. Okay, a less commonly used solid phase material in TLC is alumina in the form of aluminum oxide. So I want you guys to find about this. Okay, so like I say, if we study the differences, we can understand better. So I want you guys to study why the silica gel can provide, is more common compared to alumina. Okay. Okay, here's the TLC mechanism. For example, here is the mechanism of this Silica. Okay, here we have the silanol. Okay, if we look over here, silanol contain the OH group as the active site, so it can produce the hydrogen bond with the analyte. So the analyte, which is the stronger the more polar the analyte, the stronger interaction with the this bond lah. So it can produce the nitrogen, oxygen, which is the hydrogen bond. Okay, very simple, right? Maybe the question is like, is it what kind of interaction with this? So you need to be able to answer what kind of interaction. It's very simple answer, but maybe some of the student will not are not able to remember. It's actually the hydrogen bonds. Okay, here is one of the reason. Okay, here is the third reason actually. Why silica is more versatile compared to alumina. Okay, so two reasons actually I already described before this, but I need you guys to be able to answer in the next discussion. So there are three reasons. Okay, here is the third reasons. Okay, in the silica, okay, if you would like to increase the activity of the silica, okay, the active site, so we can just play around from 150 to 200 degrees Celsius. But for alumina, we need to heat, okay, the plate of alumina at 1000 degree, at about 1000 degree, before we can have more increment in the activity. So here is the third element. So please state the element here. Maybe I will ask later on, maybe in your homework, and maybe from the at our next discussion later on. Okay, the next item that we will look is the mobile phase of the TLC. Mobile phase competes with solutes to interact with the active sites on the adsorbent stationary phase. Elution power of the mobile phase increases with its polarity. Okay, so mobile phase competes with solute. You can imagine like, okay, here maybe I can draw better. Okay, maybe the compound interact. So your mobile phase, you can imagine the triangle as the mobile phase. The stronger the mobile phase interact with the stationary phase, it can replace the solutes, so the solutes can move upwards faster. Okay, so in term of the TLC and also paper chromatography, since the surface is polar, the stationary phase is polar, so you need the stronger interaction of the mobile phase to replace the analytes, to make the analyte move faster. Okay, but not again. I say it's just in the theoretical. If you want the analytes to move faster, so you need to increase the polarity. But in the most situation, we don't want them to move faster at all. If they move faster, really fast, so what happen is that it will not be separated when or we cannot calculate the RF value. Later on, I will discuss about the RF values. But it's not necessarily we need the elution too fast. Okay, but here I just described it theoretically. Okay, how to increase the elution power. To increase the elution power, we increase the polarity. If you want to reduce the elution power, we can reduce the polarity of the mobile phase. Okay, so here is just the theoretically how actually the mobile phase work. So, but don't misunderstood that we need to have a strong polarity. It's not necessarily. Okay, same goes to the Hplc later on. It's not necessarily we need the stronger mobile phase. Okay, it depends on our analytes. Okay, so if you look over here, if the mobile phase is strongly attracted to the absorbent, the solvent will displace the solutes. Okay, if the mobile phase is strongly attracted to absorbent, if the mobile phase is strongly attracted to the stationary phase, the solvent or the mobile phase will displace the solutes. Solutes mean our compounds or our analytes. Why it means by solutes? Okay, solutes because we are not, we can, it's not only our analytes. Maybe in the sample, it may have other kind of the compounds. That's why mentioned here as the solutes. So mobile phase strongly attracted, so the mobile phase can displace, okay, the solute faster. Okay, so what happened? Okay, the solute will move at the rate as almost the same with that of the solvent. So if your mobile phase is too strong, okay, mobile phase is too strong, what happens is that your analytes will move at the same rate with the solvent. Okay, okay, what happens is, okay, let's say here is the TLC plate. Okay, your solvent begin here, right? If your mobile phase is too strong, if your mobile phase too strong, maybe after 10 minutes, okay, your analyte start here, your mobile phase, after 10 minutes, your mobile phase will reach this level. So if your analyte, your mobile phase is too strong, what happen? That the spot also will move at the same distance with the solvent. Okay, if that happen, it means that our solvent need to be reduced in polarity. Why we cannot say we want at one? Because if the polarity, if the analytes or the solute move faster, so we actually want the compound, the solutes interact with the station phase. Okay, if it's not really interact with the station phase, it's not why we bother to use the TLC. Okay, so we need to adjust the polarity of the solvent. Okay, that's why we don't need. It's not necessary. It's not necessarily we need the a strong mobile phase. Okay, so what can we use? Maybe we can use Smith's mobile phase to adjust the polarity. So maybe after, okay, okay, maybe after 10 minutes, the eluent come here. Maybe the compound, okay, is spread. Why spread? Why I cannot draw? Okay, maybe it's spread up to here. So it means that is intermediate polarity. Okay, later on we will look into the RF value, or we call as the retardation factor. Okay, before we going to that, okay, I think retardation factor, yeah, still long after that. Okay, but just, okay, here is the example of the eluent strength. Okay, the more polar of the eluent, okay, the more strong the mobile phase. Okay, so for example here, the polarity of the pentane. Okay, pentane is non-polar, so it's not that great compared to the water. Is almost 1.0. Okay, metal is 0.73. If you look over here, it increase with the polarity. Okay, a good solvent system is one that move all the components of your mixture of the baseline but does not put anything on the solvent front. Okay, what is mean by the solvent front? Okay, solvent front, for example, the one, for example, solvent U start from here, okay, and then end up to here. Solvent front is where is your solvent stop. Okay, when your analysis in 10 minutes, for example, your solvent front reach here, your solvent, and here is your solvent front. So your solutes, okay, the best, a good solvent system is not is the sorry is the solutes that move between, okay, where the solvent begin and before the solvent ending. Okay, it means until the solvent front. So your mixture of the baseline, here is the baseline. Okay, you spot here. Okay, so it's actually move a little bit further, but not that far until it reach the solvent front, or where the solvent ended, move ended. Okay, so in the HPLC, you are never allowed the solvent to reach the end of the plate. Never. I say again, you are not supposed to allow the solvent to move until the end of the plate. Usually, we stop the interaction when the solvent reach 1 cm at least 1 cm below the end of the solvent plate. So the at least the distance here must be 1 centimeter. You cannot allow more than that or reach the end of the plate. Please don't do so. If you are doing so, it means that it's not a very good practice. So maybe I will ask later on the question, okay, why we cannot to allow the solvent up to reach the edge of the TLC plate. Okay, so the RF values later on we will look into that. So here's the thing: very positive, methanol, ethanol, propanol, moderate polar. So you can use external chloroform dictator, maybe non-polar, saturation, petrometer, blah blah blah. So you can use the combination, okay, to make the polarity become intermediate. Okay, here is the example. Okay, so let's look into the procedure for the TLC development. Okay, small quantity of solution of the mixture to be analyzed is deposited as small spot on the TLC plate. Okay, basically here is the spotting line. Okay, the sheet is then placed in the chamber containing a small amount of the solvent. So maybe okay, at here you spot the sample. Okay, maybe if we look at the front view, maybe here you spot the sample. The solvent must be lower than the spotted sample height. Okay, so for example, the solvent should never pass this line. Okay, should never. The solvent, okay, gradually move up the plate via capillary action, and it carries the deposited substance along with it at the different rates. So the solvent will move up by the capillary action, so it will move the solvent, okay, based the movement of that depends on the interaction with this tertiary phase. Okay, I think I already discussed, if you put a stronger solvent, it's not necessarily is good. Okay. Okay, the desired result is that each component of the deposited mixture is moved at a different distance up the plate by the solvent. The desired result is that each component of the deposited mixture is moved at a different distance up the plate by the solvent. So if you look over here, the desired result, each component, for example, we have three components over here. So we need them to move at different distance. Okay, the problem is, if for example we have three compounds, but let's say because of the the solvent is too strong, they move as the single spot, so that is not a good one. We need each of the component separated, okay, and move at different distance. Okay, if for example we have three components move at one distance, it's not that good. It means that our TLC is not that good. Okay, the chosen what we call the selection of the morphes is not that good. Okay, it's not okay. The components that appear as a series of spots at different locations up the plate, that we call as the, okay, sorry, the components then appear as a series of spots. Okay, if the components are separated and move at different distance, okay, because they have the different interaction with the tertiary phase, so we can observe in series of spot. Okay, for example, there, if the components is only one, the component only one, for example, pure standard, you can you're supposed to see only one spot. Okay, the RF values of standard and samples are then calculated. Okay, then you compare between standard and also sample. Okay, just as described before this, maybe here is your sample. Okay, maybe here is your standard. Maybe after a while, then your standard move here, is mean that we know that your sample also, probability that your sample also have this compound is high lah. Okay, if for example your standard here, okay, it mean that your sample do not have this compound. Okay, okay, here is the another figure of how we actually can set up the mobile phase. So TLC plate you spot, okay, you spot on the TLC. So the plate is placed in a chamber containing small amount of solvent. The solvent is gradually moved up the plate, okay, via calibration, carrying the substance along. Okay, so if we look over here, okay, the solvent is low compared to uh, the line that you spot. Okay, then the solvent will move gradually. Okay, to have a better separation, for example, if your TLC plate is just 2 cm, okay, then you stop. So if you look over here, even though the color is different, but the distance is about the same, so it's not a good thing. So to have a better separation, okay, you need to have the longer TLC plate. Okay, if you look over here, okay, here is the solvent front. okay, here is your sample. Okay, if you look after a while, we can see the differences between the movement of the spot. Okay, this one just move here and here, here and here. So if you observe the RF value, okay, later on we will learn about the RF value. Just now we just observe, okay, they have different components. From the spots, we see the same thing, right? Okay, for example, here from the gel, what we call the gel ink from the brand A. Here is the gel ink from the brand B. Okay, so maybe you wonder what kind of the application. Okay, for example, okay, the one we obtain in the forensic application, I can just give an example from the forensic application. Maybe we would like to compare the ink obtained from the crimes from the suspect. Okay, so we perform the Tlc plate. Okay, the one that we obtain from this sample. So if for example they produce the same what we call spot, okay, spot pattern, this means that the probability that the sample, maybe the hand check writing, okay, that the what we call adulterated, okay, or maybe the tempered with the suspect use the same ink material is possible. So that is the kind of example that I can give to you. So how we can visualizing the chromatogram? Okay, if it's colored, we can see by our naked eyes. For example, the one that we spotted over here, we can just see by our naked eyes. If not, okay, we can use the UV lamp. Okay, so usually what I will do is I will try to use the UV lamp first. If the UV lamp not providing a very good what we call observation, then I will what we call use the chemical enhancement. Okay, for example here iodine, okay, or concentrated sulfuric acid. Okay, it will react with all organic compounds. It will produce brown or black spot in hydrogen. Okay, for example, if we would like to synthesize maybe 1 degree or second degree amines, so it will produce this kind of color, purple and brown. Fluorescein, okay, okay, you can use fusion for magenta, concentrated sulfuric acid, and 2-DNPH. Okay, so here is the example how you can visualizing the spots. Do you need to remember everything? No. Maybe you can just try to remember the easiest one, the most what we call utilized, usually the iodine vapor, okay, and also hydrogen. Okay, this is the most common one. Okay, for the chemical enhancement. But for the visualizing the spots, you can describe treating first by the naked eyes, if not using the UV lamp, and third one using chemical enhancement, for example, using the iodine vapor or concentrated sulfuric acid. Okay. Okay, that alone can give you 3 marks if the question asks in the test or quiz or final exam. Okay, the next one we will look into the RF value or retardation factor. RF value for a substance is the ratio of the distance that the substance travels to the distance that the solvent travels up to the plate. So it means that we measure the ratio, the distance between your movement of the solutes or the components to the distance of your solvent front. Okay. For example, you would like to measure the RF value of this blue. So you measure the distance over from the spotted here to here. Okay, and then you divide it from the distance of the solvent here to here. Okay. See, if you look over here, dx is the distance of the components. 1 cm, for example. Maybe from the solvent front, move from here to here. So maybe move about 4 cm. So 2 over 4 is 0.5. Our retardation factor is 0.5. Okay. Okay. The base ratio is between 0.15 and 0.18. It means that it's off of the baseline and is not that near to the solvent front. Okay. So RF is the retardation or retention factor. Okay, that is the definition or the full of the acronym of the RF, or how far up a plate of the compounds travel. RF values can be used to aid in the identification. Okay, why I say it? Okay, not really confirm. So it just can help you, but not really confirm. Okay, that's why in the JKM Jabatan Kimia Malaysia, for example, they want to analyze drug. Okay, for example, they will analyze using the TLC because the TLC is the cheapest one, and then they need to confirm with the analytical instrumentation. Okay, why they cannot just uh, use the TLC? Okay, the TLC can only help in the screening. Okay, again, I repeat, TLC can only help in the screening. Okay, compound A, okay, the RF value might be the same with the compound W, the RF value. Okay, that's why we can only screen the possibility that the compound is the same, but we cannot really confirm, okay, that the compound is really the same. Okay, that's why I mentioned here the RF values can be used to aid in the identification, okay, by comparison to the standards. Okay, the next one is the RF value is not a physical constant. Okay, and comparison should be made only between spots on the same sheet runs at the same time. Okay, okay, here is the other thing that I need to remind guys. RF value is not a physical constant. Okay, the one that you analyze today. Okay, for example, you analyze today in the morning, and then in the afternoon you run another plate. You might get the same RF value, but the probability you get the different RF value also there. So RF value is not a physical constant. It's not, for example, today you get 0.5, later on when you run at the, for example, Johor Bahru, you run at the, for example, in Turkey, for example, maybe at Manchester United, okay, it may not be the same. Okay, so it's not a physical constant. It's not necessarily we will get the same. So whatever it is, the comparison should be only made on the same sheet and run at the same time. Okay, first, you cannot, for example, uh, my drawing, okay. So for example, you have two chamber. Okay, for example, okay, you want to do like this. You have two TLC plate. Okay, because of the standard is a lot, so you decided sample you run at different chamber. Can we compare between this? Cannot. We need to compare at the same sheet and run at the same time. Even though the size of the beaker is the same, the size of the TLC plate is the same, the solvent is the same, you say the same, but when you do this kind of the comparison, it's no longer valid. It's no longer valid. Okay. Okay, so you need to run at the same time as well. Okay, you cannot spread them. Okay, you cannot run one in the morning, one in the afternoon. Okay, you cannot do that. Okay, two substances that have the same RF value may be identical. Those with the different RF values are not identical. So we can say that the one that have the similar RF value. So we can say they may be identical. Okay, it may be that compound, but we cannot confirm. But of course, the one that have different RF value, we can say that pretty sure they are not identical. They are not the identical at all. If they are the same, we can say is the probability to be identical is yes. But if they are not the same, we can say very sure they are not the same. Okay. So here is how to calculate the RF value. Distance travels by the analytes. Okay, distance travel by the solvent front. Okay, maybe the solvent front just a little bit lower. Okay, example. Okay, so sometimes the student ask me, okay, okay, for example, you spot here, but solvent you put here, okay. So based on my reading, there are actually two ways where you calculate the RF values. Okay, the distance of the components you can measure from the starting line. How about the solvent? Okay, because the difficulty of the solvent, because we need to observe where the line actually the solvent begin, but that will be a problem. So based most of the books actually they begin to calculate the distance of the solvent front starting from the line of the spotting. Okay, so you need to standardize the method. of the distance traveled by the solvent front. If you ask me, I will start my solvent front distance the same one with the one that you start the distance of the analyte. Okay, so if you analyte spotted here, you will solvent front also I will measure here. Okay, so basically it will produce the same result if you compare the RF value here and the RF value of this compound. For example, we have another one. Okay, so I think that is the best one lah. Okay, because it's more easily to observe if you compare the one that actually low than this line. Okay, of course you need to make the solvent less than this line. Okay, why? Okay, I think I have already put that into your task. Okay, you need to describe to me why we need the solvent to be less than the distance, the height of the where you spot of your sample. Mana yang you letak you punya sampel, kenapa the solvent kena lagi rendah. Okay, macam saya, tapi untuk pengiraan distance travel by the solvent front, saya lagi prefer untuk kira daripada di mana titik spot tu bermula. Sebab sebenarnya di mana titik kita bermula tu kita akan letak line, so kita senang nak measure mana distance tu begin. Tapi kalau kata solvent front kita start sini, okay, susah sebenarnya dalam chamber tu nanti you nak ukur berapa cm sebenarnya solvent tu dalam you punya chamber, so it will not be easy. So saya akan start juga dengan starting line, so itu lagi mudah. Okay, here is the class activity I will ask later on in your class discussion later. Okay, let's continue. Okay, before that, good afternoon. Okay, let's look on the differences between thin layer chromatography and also paper chromatography. In thin layer chromatography, the principle of separation is by adsorption. It means that the analyte's interaction between the station phase of the TLC is solid. So the interaction is on the surface of the stationary phase, which is the solid particle. But in the paper chromatography, because within the cellulose we have H2O, right, fill in within the interspace, so the interaction between liquids, so we call as the partition. Okay, more amount of substance is required for the thin layer chromatography, where paper chromatography less amount of substance is required. So here is the amount of the sample. Okay, in the thin layer chromatography, we need to put just an enough amount. Okay, because the thickness, okay, of the thin layer chromatography allow more sample to be loaded. But for the paper chromatography, we cannot put very much in the paper. If we put so much in the paper, what happen that your sample will get diffused, okay, to the surrounding. That is one of the weakness of the paper chromatography. Why nowadays paper chromatography is never been used, especially to look at the qualitative. They just perform using the paper chromatography, just wanted to know, is there multiple compound inside there. That's it. But never go until the retardation factor. They never do for the comparison. Okay, they just want to know, screen, or is there any extra compound? Is there any extra band of the color based on the paper chromatography? Okay, for the thin layer chromatography, okay, for the process of one plate of the TLC is much more faster compared to the paper chromatography. Okay, it may take minutes and also hours, but it's actually faster than the paper chromatography. Okay, I have performed the TLC which take hours because my TLC is plate is longer. It's more than 30 centimeter, so it will take longer. Okay, in that situation. But normally, if we compare between them, okay, for example, if the TLC is supposed to take 45 minutes for that particular length, in the paper chromatography, it will take a longer time because the paper chromatography is much more what we call the strength, the interaction is much more stronger. Okay. And aspiration of the TLC is much more sharp. It means that, for example, the dot, okay, the spotted, okay, here's my pen. Okay, for example, you have this spot and then it transfers into very beautiful spot. Okay, but for the paper chromatography, you can see like a diffusion. Okay, it's not that clean. Maybe maybe we can look again in the, sorry, At the figure of the paper chromatography, do we have? Alright. Oh dear, I don't show you. Hopefully I have. No, I don't. Okay. Here, okay. The paper chromatography, okay, it's not forming a very good spot. So just give you band. Okay, the band or band of color. Okay, if we compare to the TLC, okay, we can see a sharp spot. It means that the separation of the TLC can provide a better separation. Okay. And then thin layer have physical strength. Ascending techniques are preferred for this type. Okay, it means that the flexibility of the TLC is much more sturdy. So you can apply the application of the TLC via ascending techniques. Mean that the solvent can perform from below. Okay, but for the paper chromatography, as I said before, because of flexibility, okay, the basic setup is via hanging, or we curl the paper, like have shown before this. Okay, like here. Okay, we either need to hang or curl vertically. Okay, so in the old, if you found in the old books, for example, okay, the other techniques to perform the paper chromatography technique is via descending technique. It means that the solvent are dropped slowly on top of the okay, for example, we set up the paper like it. Here you hang, okay, to increase the time, okay, to reduce, the time taken to process the paper chromatography to complete, so maybe they can spot the sample from above and then they drop the solvent. So by allowing gravitational force and by additional of gravitational force, they can fasten, increase the speed of the TLC paper chromatography process. Okay, that is the other setup. Okay, the basic setup, okay, is either by hanging or also curl, and then the solvent is at below. Okay, that is normal setup and will take a long time. But if you want, for example, to increase the efficiency of timing, so we can do like this. Okay, and what are the others? In TLC, chromatoplates are prepared by coating thin layer of silica gel or alumina on the glass plate. Okay, it can be either glass plates or alumina plates, or aluminium plates, and also the plastic plates. Okay, nowadays also available in plastic plates. Okay, just for the information. Okay, and but the paper just generally use what may filter paper, silica gel or alumina cannot be used. They cannot be made into sheets. We cannot attach. We cannot what we call synthesis that silica or alumina on the surface of the paper because it's not sturdy enough. Okay, in TLC, corrosive reagents may be coated on the glass plate. Okay, that is the best thing. Okay, for example, you have some corrosive solvent as well. Okay, or corrosive analyte as well. You can test using TLC. But if, for example, your analyte is a little bit corrosive, if you put in the paper, of course, it will destroy the paper. That's why that's the other way. That's the other reason. Sorry, that's the other reason why thin layer chromatography is much more preferred compared to paper chromatography. Okay, sensitivity of detection of the fracture is high. The spots are less diffuse, less sensitivity of detection. Spots easily diffuse. Okay, I think it's refer the same point with this. Okay. Okay, TLC can be evaluated under UV. Paper chromatography cannot be evaluated under UV. Okay, TLC, because we have this silica at the background, it can produce a better observation, okay, under UV light. But under chromatography, the glowiness, okay, it's not that, significance, okay, to be looked under UV. Okay, that is about delay chromatography and paper chromatography. So the question can ask you state the differences between both, and why do you think the paper chromatography have disadvantage compared to thin layer chromatography. Okay, that is the other kind of question. A lot of kind of question can be asked, even though this topic is kind of very simple. Okay, but have a lot of the question can be asked. Okay, so be careful and please understand very well. Okay, advantages of the Hplc is simple, quick and cheap, economically priced disposable plates, no extensive sample cleanup, ability to detect wide range of compounds cheaply, non-destructive detection, high throughput, 2D and multi-dimensional, easily carried out without great expense. Okay, for the TLC, it's very simple, quick and cheap. Okay, so it doesn't need that the person is really expert. Okay, so very simple, quick and cheap. The plate also is not that pricey. For example, if you run, okay, in the outside HPLCMS, so it will cost you about 300 ringgit. If you buy TLC plate 300 ringgit, maybe you can get 100 sets of it. So economically priced, okay, cheap lah. Okay, no extensive sample cleanup. Okay, in HPLC we need to perform a very good sample preparation. We want to avoid background to appear in the chromatogram, and maybe the other thing we would like to avoid that our instrument to be damaged. Okay, so we need to prepare our sample very carefully. We need to prepare our sample very carefully. Okay, but in the in the TLC, the sample preparation is not that particular. Okay, ability to detect wide range of compounds cheaply. If you have the standards, yes. Okay, then we can do the comparison. Non-destructive detection. Why I said non-destructive detection? Okay. Okay, so basically, in Jabatan Kimia Malaysia, I give the example based on the forensic point of view. Okay, for example, here is the sample you obtain from the supplier of the drug. Okay, here is the standard one, here is the standards two. Maybe here is the cocaine, here is the amphetamine. Okay, so what you can do, okay, you get the impurities, you get the spot like this. Okay, and then the standard go like this and here like this. So what you can do, okay, like I said before, the TLC is only used for screening. Okay, from the TLC plate you can scratch this. Okay, you can scratch this spot, and then you can dilute in the solvent, and then you can run for the HPLC or GC. So in Jabatan Kimia Malaysia, in court, okay, the analysis need to be done at least twice. Okay, either of this by screening and also confirmatory technique. So TLC is part of the screening process. Okay, so we can use, okay, it's actually non-destructive. It mean that we can still, okay, take the spot and further proceed with the further analysis. But for example, if we just run the sample under HPLC or GC, the sample will get destroyed. We cannot collect the sample anymore. Okay, but that's why, okay, in the forensic principle, always goes to non-destructive technique first. Okay, in the forensic, always goes to non-destructive technique first. Then later on, we go to the destructive techniques. So we screening first, and then we proceed with the destructive. That is the what forensic analysis, okay, has been practiced day to day. Okay, then high throughput. Okay, that is about same about this point. Okay, 2D and multi-dimensional, easily carry out without great expense. Okay, we can refer same about the first point. Okay, very simple, no expertise is required for this. Okay. Okay, now let's move to the next part. Okay, we settle on the planar chromatography. And the planar, we have the TLC, also paper chromatography. So let's look on the liquid column chromatography. Okay, just right. Okay, so here is the example of the column chromatography. If you look over here, above here, we can see the solvent. Okay, and then inside here, we can see the band. Okay, the sample here may be the brownish in color, reddish, dark brown in color. So we can see the band. Okay, so inside here we have this silica stationary phase. Okay, we can use alumina as well. So the stationary phase is placed, or we can pack in the vertical column. Okay, the vertical column usually made of glass. Okay, because why we made of glass? Because we can see, observe by our naked eyes. Okay, the column length, the column ID, absorbent phase particle, this you are not necessarily to remember, because I will not ask you guys exactly what is the column range, what is the ID of the column, what is the diameter of the absorbent particle size. That is the thing that I also would hate, okay, if I'm a student, to remember those very exact detail. Okay, but you need to understand. Okay, for example, the ID is bigger, so we need to put the pack material. The collar length is longer because we want to allow better separation. Okay, the absorbent particle size must be smaller because we need to pack it very well so that we can separate our compounds or our solutes better. Okay, the mobile phase is added at the top and allowed to flow through the column by the gravity or external pressure. Okay, so usually the mobile phase is added at the top of and allowed to flow through the column, okay, by the gravity or external pressure. For example, the solutes take a slower time. So what we can do, we can push. Okay, we can push by using pump. Okay, we can put pump over there, so we can push to make the solvent move, okay, faster. So with mobile phase, we put at the top. Okay, and we need to them to move our solutes through the column. If they move through slowly, okay, by gravity pressure, we can put external pressure. We can put pump on the top. Okay, generally used as the purification technique to isolate desired compounds from a mixture. So usually what the technique has been used is to purify, okay, or to isolate. Isolate is mean that we want, okay, from 10 compounds available in that single mixture, we want to take one. So for example, we collect this band, and then 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 we collect this band. So we can purify. Okay, from 5 compounds mixed together, we can separate each of them. Okay, that is the very widely been used, especially in the organic chemistry related industry. Okay, for example, in the preparation of the medicine, okay, where you need to purify a compound. Okay, that is when actually we need this kind of the technique. So if you are involved later on in the final year project, okay, involved in the uh, what we call organic synthesis, or what we call a natural product, okay, you will play around with the liquid column chromatography a lot. Okay. Okay. So carry out using column packed with particle. Okay, don't need remember about exactly about this. Okay. Long columns can result in low gravitational flow. External pressure can be applied using compressed gas or pump to enhance the moving flow. So usually at the below here, you will put the cotton wool. Okay, and then we put a layer of sand. Okay, purified sand lah, not the sand that we collect outside of our house, which is maybe we can observe the poo of our cat. No, not like that. So wool, okay, maybe that after the wool is the pure sand, okay, purified sand lah. Okay, and then after that, okay, after that we put our stationary phase. Okay, stationary phase is the silica or alumina. Usually we mix with the water to make it slurry so it can pack better. Okay, of course you can put the stationary phase without you mix with the water, but the problem is that it will take too of course later on you need to put the mobile phase to condition the pack material, of course. Macam mana senang kata, kalau kata kita tak campur dengan air, nanti pun kita kena lalukan dengan mobile phase juga sebab nak bagi dia betul-betul pack. Okay, so that's why kalau kata you tengok nanti dalam video link yang kita akan bagi pun, dia akan jadikan slurry dulu, maksudnya dia akan campur stationary phase tu dengan air, lepas tu baru dia tuang. So from here actually he just put the stationary phase and then put the what we call the solvent later on. Okay, now he load the sample. Okay, maybe before that, okay, maybe you can found from the other video, or maybe found from the journal, they put another layer of sand. Okay, maybe sometimes they just put directly the sample. Okay, why they put sand above? Okay, because they don't want, because the particle of this stationary phase is very small, and then the density is not that high. So if we put the what we call the mobile phase too fast, that the stationary phase pack will bergerak lah, move downwards and upward. So to make sure atas dan bawah tu maksudnya terjaga dia punya pack dia tu, so they sometimes they put another pack another layer of purified sand Then after that, they loading the sample. Okay, but for these figures, they just after they put the station phase, they loading with the uh, they conditioning with the mobile phase, and then they put loading the sample here, and then after you load the sample, and then you put your solvent. Okay, after that you allow it to what we call further to flow, okay, to separate. Okay, if for example the separation is too fast, you need to adjust the this flow, okay, the speed, so they will move slower. Okay, so this thing, okay, if okay, then you can collect the uh the compound, the desired solutes, okay, on this spray container. Okay, so very easy, right, for the column chromatography. Okay, the column is packed with the station phase and then incubated with solvent. The sample is loaded. Okay, the morphine is added and allowed to flow to the column. The separated components are collected at the end of the column interval. So is is the kind of the question can be asked. Okay, for example, please describe the procedure, or maybe please illustrate the procedure. It can also be asked. Okay, maybe it can ask, okay, after you did this, what you supposed to do. Okay, how actually the classical column, how actually the column chromatography is useful in the world of the chemistry. What actually they benefit to? What is the application? There is a lot of kind of the question can be asked. So please understand. Okay, very well. Okay, classical color chromatography is useful in the separation of samples that can be separated easily at high quantity or preparation scale level. Okay, if you look over here, you can see how big is the column. Okay, how big and how long. Okay, him, I think, because he was orang putih. I believe he already passed away. Okay, maybe he was about 2 meter plus maybe 2.5 meter. This column alone. Okay, the diameter is very big. Okay, maybe it reach to 25 centimeter, the diameter. Okay, if you can imagine like this, how they purify. Okay, and here is the advantages and disadvantages of the liquid column chromatography. CC is advantageous over most of other chromatography technique because it can be used to separate and purify substantial quantities of components from a mixture. So compared to the other chromatography technique, okay, the liquid column chromatography is used, okay, it has been used to purify, okay, compound at large amount. Okay, a TLC only able to what we call we want to look either is purified or not, but to purify and to collect at higher amount, okay, liquid column chromatography is one of the method, okay, other than what we call we collect by the distillation or uh, the other, for example, the density or separation. Okay, but liquid column chromatography is one of the technique, okay, in especially in chromatography. Okay, but the other thing, for example, the temperature or the distillation or the density is the other story. Okay, the disadvantage, packing of the column requires some technical skill. Okay, if you don't pack it very well, okay, what happened that, okay, like I said before, the packing material is not well packed, so it will move, that it will disturb, okay, the process of dispersion. The technique is time consuming, okay, because it will take a lot of time, okay, to prepare the column, especially when you deal with the larger column that like this person, okay, and requires large amount of solvent. Okay, if you look over here, I believe you use liters of solvent, gallons of solvent. Okay, if you use the harmful solvent, of course it will harmful to you. It requires constant attention while the experiment being performed. You cannot leave you cannot left the laboratory or the experiment, so you need to be there where to collect all the what we call the solutes that you want, okay, or the compounds that you want. The collection vessel must be frequently changed, and solvent should be added continuously to the top of the column at rate sufficient to cover the adsorbent. Okay, of course we can automate it, but collection vessel must be frequently changed. Okay, because of course we use a lot of solvent, right? So we need, for example, kita dah collect 2 mil pun masih tak sampai-sampai lagi band ni. Maksudnya macam, oh, ni jauh sangat, kita collect penuh, so kena tukar. Kalau tak melimpah, okay, jatuh atas lantai, nanti lantai rosak ataupun contaminated. Okay, So that is kind of the advantages and disadvantages. So advantage and disadvantages. So you need to remember. Not remember lah, you need to understand. I don't like to use the word remember. You need to understand. Okay, if you can understand, you can remember it better. So here is the link, later on I will provide to you. And that's all for this topic. Okay, in the next week, okay, we will have what our discussion. You can ask anything about the planar and also column chromatography. That's it. Thank you. Bye and assalamualaikum.